Welcome back, students. So, on this video, we will look at our different ways of measuring concentrations, ways to convert them back and forth, and we'll be doing the math related to them. So, bear with us as we go through this. Now, we will measure concentration in many different ways. We've already learned in previous videos how to measure concentrations in molarity, but that isn't always appropriate in all situations. Sometimes most people don't understand the concept of molarity, but most people might understand percent by mass. We can also measure things in mole fractions and molality, which is a real stickler. Molality instead of molarity, which is molality is lowercase m as opposed to capital M. As I said, percent by mass is easy to measure, especially if you're only using a balance. That you can measure, like I weighed out this, I weighed out, here's the total mass, I can figure out my percent by mass. Mole fraction is very useful for measuring things that are mixed in proportional quantities just by using the moles, and it's very useful for certain gases and liquid-liquid mixtures. And molality, while being similar to molarity, is temperature independent. It is a value that is independent of temperature. Molarity, because it is dependent on a volume, and a volume changes density at given temperatures, so the volume can expand and contract if it gets hot or cold. So molarity is always going to be varying if you do it at temperatures other than 25. Molality will stay the same at all temperatures, which will be important for some later calculations. So the first one, mass percent and mole fraction. I will do them together because they're pretty similar and pretty easy. Mass percent is given on, for example, hydrogen peroxide bottles. Like you can buy hydrogen peroxide in the store. It's going to be usually something like 3% by mass hydrogen peroxide, which you're like, oh, they're really gypping me. 3% by mass, that's a lot of water and not a whole lot of hydrogen peroxide. It's probably a good thing, because if it's fully concentrated, you'd be burning yourself and hurting yourself all the time. Same thing with vinegar. Vinegar ranges between 5 and 10% active ingredient of acetic acid on the bottle when you buy it. 5% by mass, 10% by mass. At higher concentrations, it is dangerous, but at 5 and 10%, it's usually pretty benign. But so we've done percent by mass before, that essentially it's the mass of a part over the mass of the whole. Percent by mass would be, in this case, the mass of the solute, which is a part, over the mass of the solution, which is the whole. The solution is the solute and solvent together. When calculating the answer, remember the 100% does not limit the significant figures. 100% is just part of the number when we're converting it. So the sig figs of the mass of the solute or the sig figs of the mass of the solution will always control the sig figs of our percent by mass. Now, a mole fraction has done something very similarly. The only difference is instead of dealing with grams, we're doing with moles. So we can look at the moles of solute over the total moles of solution. Now, this could be moles of solvent as well, if we care about what is the mole fraction of the solvent. We use that typically when we need to know moles as opposed to just a generalized mass, just a generalized amount. We would use the percent by mass more often in everyday life, especially things like environmental chemistry, but mole fraction is more useful for later calculations. But it's moles of a solute over total moles of solution. These numbers do not need to be multiplied by 100 because it's supposed to be a mole fraction out of 1. It's a fractional quantity. So let's do some quick calculations. Let's convert hydrogen peroxide, which is 3% by mass, to molarity, given that the density is 1.01 grams per mil. So we'll start with that. To do this, we need to know, real quick, what is hydrogen peroxide? Hydrogen peroxide is H2O2. So with a molar mass or molar weight of 1 plus 1 plus 16 plus 16, we have a molar mass of 34 grams per mole. So 3% by mass, we need, so 3%. Here's where it helps to have a limber mind. That's mass of hydrogen peroxide over mass total times 100. Now we need to turn this into molarity, which would be moles of hydrogen peroxide over volume of solution in liters. So we can break this into two parts, but the first thing is we need to get a mass of hydrogen peroxide. But technically we're not given a mass total. So we have to figure out these, we have to make an assumption. But that 3% relates to a ratio. The ratio says if I have 1 gram of solution, I would have 0.03 grams of H2O2 per 1 gram. Or this would also mean I have 0.3 grams of H2O2 per 10 grams. Or 3 grams of hydrogen peroxide per 100 grams. All of these give us a ratio of 3%. For the sake of my brain and yours, I'm going to stick with this ratio. 3 grams of hydrogen peroxide per 100 grams. So with that in mind, 3 grams of H2O2 has a molar mass of 34 grams per 1 mole of H2O2. So what is my moles of H2O2? My moles are 3 divided by 34. 3 divided by 34, or 0.088, we'll say 24 moles. Now, that works pretty well. I need to find now the volume of solution. If this was pure water, we could just use that there's 1 gram per mil. But since it is not pure water and I was given a density, 100 grams of solution has a density of 101 grams per mil. So 101 grams, 1 mil, grams and grams cancel. There is 1,000 milliliters in 1 liter. Milliliters and milliliters cancel. So 100 grams divided by 101 gives me about 99 mils. 99 mils divided by 1,000 gives me 0.099 liters. It was 99.01 liters. Now, for the final part, the answer, molarity is going to be equal to my moles, 0.8824 moles divided by my liters, which is 0.09901. 0.08824 divided by 0.09901 gives a molarity of something like 0.89, say 12 molar. There is my answer. Now the second question. What is the mole fraction of ethanol if 30 grams of ethanol, 30 grams of, this one you need to know the molecular formula. So ethanol is C2H6O. And 15 grams of methanol, which is C1H4O, are mixed with 100 grams of water. 100 grams of H2O. What is the mole fraction? So back to the salt mines here for the calculation. Now we need to know the molar mass of each guy. C2H6, so 12 times 2 is 24. Plus 1 times 6, 6. Plus 16. 30. So 46. 12 plus 4 plus 16. That's 32. And 2 plus 16, that's 18. So we need to know what is the moles of each guy. So 30 grams divided by 46 grams per 1 mole. 30 divided by 46 is 0.6522. 15 grams divided by 32 grams per 1 mole. 15 divided by 32 is 0.4688. And 100 grams divided by 18 grams per 1 mole is 5.556. So with that in mind, the mole fraction of ethanol is going to be 0.6522 divided by the sum of our individual mole fractions, 4688 and 5.556. 4688 plus 0.6522 gives us the total sum on the bottom is 6.67, we'll say 7. So 0.6522 divided by 6.677 is 0.09, we'll say 768, like 9%, close to 10%. If I wanted to calculate the mole fraction of methanol, I would use the 0.4688. divided by the 6.677. That would be the methanol. That's ethanol. Methanol would be 0.07021. That's methanol. And of course, water with 5.556 divided by 6.677 would be something close to 0.8321, like almost 83% of the moles. So it's taking up the majority of the mole fraction. Okay. Now, molarity. We've already talked about molarity, but a quick refresher. Moles of solute over liters of solution. Moles of solute over liters of solution. So it's moles of the part over liters of the total. I only specify that because look at molality. Molality is different in one very, very important regard. Instead of caring about the quantity of solution, we look at the quantity of solvent. Molality is moles of solute over kilograms of solvent. So you're essentially weighing out the solvent and mixing it in. Because when you heat things up, density changes. The mass doesn't change, but the volume does. So as long as you're measuring the kilograms of solvent, that number is not changing. So molality is particularly useful in sensitive chemistry where temperature changes, especially where it can change drastically in the next section when we talk about colligative properties. But molality is independent from temperature, unlike molarity. So I just already went over that. Now let's look at this. If I need to convert a 2.5 molar solution of sulfuric acid to molality, what is that? So 2.5 molar, and the density is 1.11 grams per mil. This one's a little tricky. What things you got to keep in mind is we're turning 2.5 moles in a liter to whatever moles per kilogram solvent. Because this is solute plus solvent. And to do this, you also need to know what sulfuric acid is, H2SO4. The molar mass, you'll see why we need this in a minute. 1 times 2 plus 32 plus 16 times 4. It's 64. 98 grams per mole. So once again, we are not given a total volume, but we can use a ratio, and that will work just the same. So that's 2.5 moles per liter. That means I could have 2.5 moles in 1 liter of solution. That's probably going to be the easiest thing to work with. So I'm going to need to turn moles to moles. Well, that's easy. That's 2.5 moles. But I need to turn liters of solution into kilograms of solvent. So that's going to be the hard part right there. The first thing I need to do is to turn liters into grams, or liters into kilograms. You could say that this is kilograms per liter, which is the same as grams per milliliter. So 1 liter with a density of 1.11 kilograms per liter would have a mass of 1.11 kilograms. Now you'd think, okay, I just take this and divide 2.5 by 1.11. But this is solution, which is solute plus solvent. So we just need the solvent, not the solute. So we need to subtract out the weight of the solute. But how do we get the weight of the solute? Well, we have a moles. We can figure out how much does that moles weigh. So 2.5 moles of solute would weigh, how much would that weigh? At a molar mass of 98 grams per mole. 2.5 times 98. Of course, then turning that into kilograms, there's 1,000 grams per 1 kilogram. Would weigh something like 0.245 kilograms. So the mass of solvent would be 1.11 minus 0.245. 11 minus 0.245. So the actual mass of our solvent is 0.865 kilograms. So our molality is going to be equal to 2.5 moles divided by 0.865 kilograms. So 2.5 divided by 0.865. And that'll give me my molality actually is closer to 2.89. We'll say 890. Little n. So that is that. Okay. So as I said, that is a little bit trickier. It's difficult to turn molality into molarity, or vice versa. It's a lot easier to calculate it from the get-go. Because how could you do this? I weigh out the solvent separately. I weigh out the solute separately. I combine them together. Or I weigh out the solute. I add the solvent and calculate the total mass, in which I can subtract them separately to find out how much solvent I added. So either way, it's a lot easier when you're measuring it in a lab than it is to measure it in person. Than to convert. So here's a quick summary of all four and how to convert between all four. We have a molarity, which is moles of solute over liters of solution. We have mass percent, which is grams of solute per grams of solution. So we can use density to get liters to grams. We can use molar mass to get moles to grams. Molality, which is moles of solute over kilograms of solvent. You can just subtract out the solute from the solution. And mole fraction, which is moles of solute over total moles of solute plus moles of solvent. So the total moles of solution. So in most problems, we will need the molar mass. And most problems, we will also probably need the density. But those will be typically given. So it's not something you would need to find out. Now this last problem for the video is if we have standard E10 gasoline, contains about 10.5% ethanol by mass. 10.5% percent C2H6O by mass. What is its molarity? What is its molality if the density of solution is 0.7489 grams per mil? So a challenge problem that hopefully will reinforce these two concepts. So the first thing, I'm going to make a big assumption that I have in 100 grams of solution, I have 10.5 grams of ethanol. Solution. Because if I times that by 100, I'm going to get my 10.5%. Now I'm going to need the molar mass. 6 plus 16, going to have 46 grams per mole. Now the easiest thing to do first would probably be the molality, but no matter what, in both cases we're going to need the moles. The moles of ethanol, 10.5 grams, if it weighs 46 grams per 1 mole. 46 grams per 1 mole. If I have 10.5, I divide by 46. I'm going to have something like 0.2283 moles. Okay. Now the easiest thing to do would be finding molality. So what do we need to do to find molality? We're going to we need the kilograms of solvent. So we're going to take the 100 grams minus my 10.5 grams to get the grams of solvent. So this is going to be 89.5 grams of solvent. And then I'm going to divide that by 1,000. There's 1,000 grams per 1 kilogram. So you're going to have 0.0895 kilograms. So molality is going to be simply 0.2283 divided by 0.895 kilograms. Moles per kilogram. So 0.895, and that would give us a molarity of something like 2.550 for the molality. What about our molarity? For our molarity, we need to turn 100 grams to liters, and we're going to use the density to do that. So 100 grams, our density was given at 0.7489 grams per 1 milliliter. And then there are 1,000 milliliters in 1 liter. So 100 divided by 0.7489 divided by 1,000 gives me a volume of 0.1335 liters. So our molarity becomes 0.2283 divided by 0.1335. 1335, and you would have a molarity of 1.710. So the molality and molarity are widely different for these two substances. Okay. There we go. Now, let's see. Okay, and And that is where we will stop this video. On the last video, we will talk about the colligative properties of solutions.